Hello, welcome to my YouTube channel. I am Thalitakum Hutajulu from Udayana University Mechanical Engineering student. The purpose of this video was made to fulfill a linear algebra course assessment, also to educate about linear algebra. Okay, my reference book from this book, Linear Algebra, Kuldeep Singh, Linear Algebra Step by Step. Okay, now we learn about general vector space. This general vector space, there are three is a subbab. Can we learn now? This one, 3.4 dimension, 3.5 properties of matrix, 3.6 linear system revisit. Okay, 3.4 dimension. So dimension, we know the dimension, right? Introduction to the dimension. The definition of dimension is the number of basic vector or action needed to describe the given vector space V. We have the example. So let A1 and A2. What is the dimension of R quadrant? So dimension of R quadrant is 2. And example A1, A2, and A3. What is the dimension of R3? Dimension of R3 is 3. So y is 2 and y is 3. We have to know in the next example R5. The dimension from the R5 is 5. 7. Dimension from the R7 is 7, and the dimension from the R2 is 2. Dimension from R3 is 3, and dimension from Rn is n. We have to know that because dimension from the Rn is to explain that every element of or to describe the any every real scalar. Okay, we next to define infinity dimensional vector space. 3.4 find the infinity dimension vector space. In general, if a finite number of vectors form a basis for a vector space V, then we say V is finite dimension. Otherwise, the vector space V is known as infinity dimensional. So, if the vector space V consists only of the zero vector, then is it also finite dimensional? So example is there is a determinant A, B, C, and D. So dimension M22 is 4. Why? So 4 is from the 2 times 2 times 2. So this is 22, right? So from this, like 2 times 2. So 2 times 2 is equal to 4. Next to there's example. Dimension from M 44 44 is dimension of 44 is 16. So 16 from 4 times 4. So dimension of MN is a M times N. So a dimension of M times Mn is the Mn, right? We have example 2. This same example is P. Dimension of P2 is 2 plus 1 is 3. So right, 5 plus 1 is 6, right? 6, not 3. And dimension from the dimension from the Pn is n plus 1. Pn is n plus 1. This is, I mean, actually. Okay, this is some vector space and their dimension. This is what we learned previous. Rn is dimension from Rn is n. Dimension from Pn is n plus 1. Dimension from Mn is Mn, right? M times n. So every basis for a finite dimensional vector space has the same number of the vector, right? So 3.4.3 surface revisited. A surface, in the previous chapter we have already learned about the surface and set, surface and subset, right? So the surface, S, we call the S is the surface if the S in the V, right? A surface is a non-empty subset S in the vector space V with form vector space in its own right with respect to the same vector addition and scalar multiplication as its parent set V. The example, let R2 or R quadrat be a vector space and S be the set of the vector 0 in A. So this is A, 0 in A. So E2 equal 0 and 1. So this vector E2 from a basic for S, therefore dimension S times 1 equal 1. Why? Because the Y dimension we think right, like a dimension from the 0 A and this dimension from the R2 is 2, right? We think like the dimension from the R2 is 2, but this is dimension from the A2 is the 1 because A2 they're in the line from the vertical line in this, right? So S is 0A. This is a surface that's spanned by itu. So that the surface is the S is the vertical axis, Y axis, and it generates any vector in S along this line, right? So surface S, which is spanned by U, V, and Y. This is a application in the 3D. So this is a note. The general misconception is that the dimension of a space is how many entries are required to specify a vector in this space, right? So this is application in the 3D. Next to 3.4.4 properties of finite dimensional vector space. So properties of finite dimensional vector space. There are two. Any linearly dependent set of n vector from a basis for V. So B, any spanning set of n vector from a basis for V. Example, we have a determinant A, B, and C. So what the dimension of the determinant M22? We have to know that dimension is the 4, right? 2 times 2 is 4. So this is in the above list we have 3 metrics. So but we have the 3 metrics A, B, and C. Why the dimension is 4? Because the basis is 2 and 2, 1, 2, 1, 2, right? Matrix, so they cannot form a basis for matrix 2 times 2, 22. So this is dimension. We have example too, which is V. F is 0 and 2V. Be a vector space in the periodic continuous function, which is spanned by S. So S is sin x, cos x, sin 2x, and cos 2x. This is a formula, right? So solution from trigonometry, we have the identity, right? Sin 2 times x equal to sin x cos x. So the hence from the formula is given that sin 2x cos x, right? So hence the first two vectors in S are dependent. So this is a dependent. Therefore, the set S cannot be a basis. So we remove one of the vector sin x cos s x or sin 2x. The basis for the given space is sin 2x and cos 2x. Summary that we have any linearly dependent set of vector from a basis for phi in any spanning set of n vector from basis for phi. Okay, we next to 3.5 properties of matrix. 3.5.1 row and column vector. So in the chapter 1 maybe we already learned about row and column vector, right? This is a columns and row columns and row. Example, we have a B, matrix B is the R1. This is a row 1 and row 2 and row 3, and C is the column, C1 column, min 3, min 5 and min 2. Columns 2 is the 6, 2 and 7. Okay, 3.5.2 row and column space. In the row and column space, row space of the matrix A is the space spanned by the row vector of A. The space spanned by vector means the space containing all the linear combination of this vector. Example, we have the column 1 and column 2 from the. So this is, we have to know the this from the matrix M. So this is columns 1 and columns 2. All in the columns 1 is the mean, and all in the columns 2 is the positive. The start centered plate in the R3 is the column space of matrix B. Space spanned by column vector C1 and C3. Right. Okay, we have to know the columns and the rows. The row space of matrix A is the subspace of Rn, and the columns of matrix A is the subspace of Rm. So row space is the Rn and column space is the Rm. Example, matrix A is the subspace in R2, right? And matrix B is a subspace of R3, but the column space is a subspace of R2. Why? Because the rows rows in the matrix B is 3 and the columns is the 2. 3.5.3 basis of a row space. So we have the matrix A is the A1, A2. R1 equal A1. And R2 is the A2 mean 4 times A1. So R1, row 1 is A1. So this is, and R2, the A1 mean 4 times A1. So 4 mean 4 times 1. So 0, right? Number 2 is A mean 4 A mean 4 is the 4, or no. That 4 times 2 is the A. So A mean A is the 0. So right. And also the 4 times 3 is the 20, and 20 mean 20 is the 0, right? So notate this: the rows of matrix R1 and R2 are simply a linear combination of row A1 and A2. So row space of A equal row space of R. So the row space of A is in a row space of R. The row space of R is in the row space of A. Right. So row space of A equal row space of R. So non-zero rows of R are a basis. So basis for row space of R. This is non-zero rows. So this is a 0 rows. This is a non-zero rows vector from a basis for the row space of matrix A. The example, we have a matrix A. So from the matrix A, we make the like previous, A this time for mean 4 times A. So we get that R is the 1 and 2. So this is a non-zero rows. So this is the vector 1 and 2 is a basis for the row space of A. This is basis from the matrix A. So this is a application in the coordinate calculations. This is line represent the row space of matrix A. This is a basis vector from A. Example B. So B, we have the formula is A1 mean 4 times A2. So B1 or A1 is the equal to R1. So we have the vectors. So this is form a basis for the row space of matrix B. So hence the row space B is a subspace of R3. So this is a subspace is the R3. So the application from the matrix B there in the 3D. Example 2. So we have a matrix C by using MATLAB, the reduced row echelon from the matrix C is given by non-zero rows. So this is a non-zero rows. From this we have now from a basis for the row space of matrix C is a basis. It's a basis from matrix C. So this is a basis span the whole of R2. So the row space of matrix C is R2. So dimension from this is the dimension is 2. Okay, 3.5.4 basis of a spanning surface of Rn. We have U and V, the vectors in R3. So this is application in the R3 transpose, right? U transpose and V transpose. So V transpose will the U is 1, 2, and 3, and V is 4, 5, and 6. So vector U and V span the third shaded plane S in the R3. So application in the RT or 3D, right? Example, we have the determinant basis for the vector space S equals span U, V, and Y, where U 1, 2, and 3, V 4, 5, and 6, and Y 7, 8, 9. So A is U, V, and Y. This is a matrix A. So span U, V, and Y equal the row space of A. So we make the row space. So from the row space we have the non-zero rows. This is the non-zero rows. R1 is 1, 0, and min 1, and R2 is 0, 1, and 2. So this is a vector space. Vector space S equals span U, V, and Y is B equal R1 and R2. We have to note that S is a subface of R3, but is actually the plane by and can be spanned by two vectors R1 and R2. Rather, the 3 given vector U, V, and Y. Example, we have U, V, and Y. So A is the U, V, and Y. So we make to the row echelon form. we have already learned about the echelon form in the previous chapter, right? The S equals span U, V, and Y equal row space of matrix A. So step 3. What is the basis for S equals span U, V, and Y? So span, right? This is a basis for S and equal U, V, and Y. So this is also phase. Phase of R4. So dimension from the matrix is 4. Okay, 3.5.5 rank of a matrix. So this is a matrix A. So the application in the 3D matrix A will only transform vectors onto the plane snow and not anywhere else in R3. So we define the rank is the term of the dimension. Okay, we have R1 and R2. We transform to the Gaussian elimination. This is a Gaussian elimination, and we have that this is a non-zero rows. So A and R. So this is a M non-zero rows. So row rank of matrix A is M. Row rank, and rank A equal row rank of A. So the row rank of a given matrix A is the number of zero rows vector in rows echelon form matrix R, because the non-zero rows form a basis for the row space. Example: determine the rank of matrix A. This is a matrix A. So we make the transpose from the echelon rows, echelon form. So we get the non-zero rows. This is a non-zero row. So rank A is a 2 because non-zero rows from the matrix A is 2. 1 and 2. R1 and R2. Rank A equal to. So we next to 3.6 linear system revisited. Null space, so which is a linear system of equation written in matrix form as AX equal 0. By using elementary rows operation, we solve the equivalent system Rx equal 0, where matrix R is row equivalent to matrix A. Example: this is a matrix C. Determine the null space, nullify the rank of matrix C. So null space N is the set of vector X which satisfy Cx equal 0. We make like this. So the rank C is the 1. Because from the echelon form, we get the non-zero in the R1. Considering the equivalent homogeneous system Rx equal 0, we have the x plus 3y equal 0 plus x equal min 3 so we have the u is min 3 and 1. So this is application in the coordinate Cartesius. So the null space N of matrix C is all the vectors on this ACID which are solution to Cx equal 0. That the vector U span the null space and is linearly dependent, so it is a basis for N. Okay, 3.6.2 properties of rank and nullity. Nullity plus rank equal number of unknowns. So this is a columns. So we have the nullity A plus rank A equal N. That N is the number of columns of matrix A, which is the total number of unknowns of the homogeneous system AX times 0. So this is N unknowns, and this is R non-zero rows. So we get the nullity A plus R equal N, which is the nullity A plus rank A is N, and nullity A equal N min rank A equal N min N equal 0. Example, this is a determinant A. So from the determinant A, we make the echelon form. So we get the non-zero rows R1 and R2. So we substitute to the rank A equal to and N is equal 7 because the 1, 2, 3, 4, 5, 6, 7, right? The number of columns of matrix A. So the rank A 1, 2, and N is the 1, 2, 3, 4, 5, 6, 7. 5. Nullity A plus 2 equal 7. Given the nullity A is the 5, right? The 7 min 2 is the 5. Next to the 3.6.6 non-homogeneous system, linear system. So equation of the form AX equal B, where B not equal to 0, not equal 0, are called the non-homogeneous linear equations. Example, we have to know the Cx equal B, where B, this is a B, vector B, 7 and 25 transpose. So we make to the echelon, form. So from the echelon form, we have to get that. So this is non-zero rows, x plus 3y seven, which given x equals 7 mean 3. So from the example, we get the x high is the equal x in 3 and 1. So this is a application in the coordinate Cartesius. We have hence our general solution to Cx equal B is x equal x high and xb, where this is S mean 3 1 transpose and V 70 transpose. Okay, 3 mean 6 mean 4 times sorry, 3 times 0.6.4 properties of non-homogeneous system, linear system. So this is a properties. This is a ring A equal ring A or B equal N full ring. The linear system has the unique solution. So B, the linear system has the infinite number of solutions, and C, the linear system has no solution. So this is example. We make to the echelon form. So we get the non-zero rows. So we have the ring A is equal 1, and hence ring A and B is 2. Because non-zero is the 1, columns 1 and columns 2. And we make to echelon form, so we get the non-zero rows is the 3. Okay, from the example we have to know the matrix A is invertible. These are properties. Ring A equal N full ring. C, no space of matrix A only contains the 0 vectors. D, nullity A equals 0. Rows of matrix are linearly dependent. And F, column of matrix A are linearly dependent. So X if the equal homogeneous solution plus particular solution. Okay, that's my explanation about algebra linear. If I make mistake, I say sorry. And finally, thank you for watching.